In this set of notes, we're going to look more at finding minimums and maximums, introduce the idea of inflection points and optimization. So recall from example 6 in the textbook on pages 218 and 219, and this was in section 5.1, we had the following to help us find candidate for local extrema. And so what we saw there was that we could find all the points where the first derivative is equal to 0. We need to consider the points where the derivative doesn't exist, and then also we need to consider the endpoints. And so if we do all three of these, this will help us find all the candidates for local extrema. And then once we find all the local, then we could then use those local to help us then find the global. Now the problem with this method is it doesn't really help us identify whether or not we have a maximum or a minimum. It just helps us find the local extrema. And so we have some additional rules that we can use to help us determine, once we find those local extrema, whether or not they are minimums and maximums. So the first rule that we're going to look at is the first derivative test for local extrema at endpoints. And so the important part about this rule is, notice this is only going to work when we have, or when we're at the endpoints of that closed interval we're interested in. And so this rule says, suppose that f is differentiable on the closed interval from a to b, and its derivative is continuous at both x equals a and x equals b. Then we have the following rules. So we have, if the derivative evaluated at a is greater than 0, then f has a local minimum at a, whereas if it's less than 0, it's a local max at a. And then the second set of rules are for the other endpoint, or the right side endpoint, which says that the first derivative is greater than 0, then f has a local maximum at x equals b, and if it's less than 0, f has a local minimum at x equals b. So let's draw a picture to kind of help us understand how this rule works. So first thing I'm going to do here is I'm just going to draw an x and a y, or an f of x axis. And what I'm going to do is I want to consider two endpoints that I'm interested in. So we're going to be on a closed interval from a to b, and we're going to be interested in how the function behaves. And so I'm going to draw two potential functions here. The first one I'm going to draw in orange. So suppose that I had a function that looks like this. All right. So we could see, looking at the orange function, we obviously have some maximums at both a and at b. So let's talk about what that first derivative would look like at a and at b. So starting here, looking at a. So if the derivative evaluated at a is less than 0, we're going to have a local maximum. So remember that we are restricted between these 2 points. This is the interval we're interested in looking at the function at. So if we were to then draw our tangent lines, notice at this point the tangent line is going to have a negative slope. Also at this point, the tangent line is going to have a positive slope. So if we look at our two rules for a maximum, which are this rule and this rule right here, notice at point A, we have a maximum when the first derivative is less than 0. In other words, we have a negative slope. At B, we have a maximum when that first derivative is positive, and that's because we would have a positive slope. Now, if we were to draw another function, let's say we drew another function and it looked like this. So notice here, I'm going to have, with the red function, I've got two minimums. So again, looking at a point within the interval from a, we would see if we draw the tangent line, a minimum would have a tangent line with a positive slope. And so again, looking at my rule, we see the tangent line has a positive slope at A when we have a minimum. Whereas at B, if we draw a point within the interval, our tangent line is going to have a negative slope for a minimum, and that's what we see right here. So that's kind of intuitively where this first derivative test is coming from. Now, this first derivative test, again, only helps us at the endpoints. So what if we have a point that is inside of the interval that we're interested in? And so it ends up that we can use the second derivative test to help, or second derivative, to help us find maximum minimums that are not at the endpoints. And so a continuous function has a local minimum at C if the function is decreasing to the left of C and increasing to the right. And a continuous function has a local maximum at C if the function is increasing to the left of C and decreasing at the right. But what does this actually mean? Let's look at the first one here. So looking at the first one, we're decreasing to the left and increasing to the right. Well, notice that's the exact same thing as being concave up. When we have a concrete up function, we are decreasing to the left, increasing to the right. Looking at the second one. The second one says a continuous function has a local minimum at C if the function is increasing to the left and decreasing to the right. Well, notice that's the same thing as being concave down. We're increasing to the left and decreasing to the right. So really, we can use that second derivative test, which helps us test to see if we're concave up or concave down, to help us find minimums and maximums that are not at the endpoints. And so we end up with this second derivative test, which says the following. It says, suppose that f is twice differentiable on the open interval containing C. If the first derivative is equal to 0 and the second derivative is strictly less than 0, then we have a local maximum. If the first derivative at C is equal to 0 and the second derivative at C is greater than 0, then we have a local minimum. Notice that this piece right here, this is really the second derivative test for concavity. And so this is one reason that testing to see whether or not you've got a concave up or concave down function can be really useful, because it actually helps us find those minimums and maximums. So let's look at a couple different examples here. So here we're going to find all the local extrema of this function, and when x is an element of the real numbers. So the first thing we need to do is we need to find the derivative. And we've seen this function before using the power rule. We have the following derivative. And so if we go back up here to how we're going to find our local extrema, notice that we need to consider all of the points where the first derivative is equal to 0, all the points where the first derivative does not exist, and the endpoints of the domain of f. Alright, so the first thing we're going to do is we're going to determine when the first derivative is equal to 0. And we can do this by setting the first derivative equal to 0. So notice this is going to imply that 3x squared is equal to 3. Or x squared is equal to 1. So therefore, x is equal to plus or minus 1. So there are two values of x which result in a derivative equal to 0. Oops. So we know automatically we need to consider the points. When x is equal to 1 and x is equal to negative 1. Now, if we go back up to our box that we had at the beginning here, we also need to check all points where the first derivative does not exist and the endpoints of the domain of x. So for this particular example, we need to note that g prime of x exist everywhere on the reals. So we don't have any points to check for that number 2. And there are no endpoints to check. And this is since we're considering all x in the real numbers. So then the only 2 points that we really, again, need to consider are, for this example, are the x equal 1 and the x equal to -1. So now we're going to use the second derivative test to determine if we have minimums or maximums. All right, so to do that, we're going to evaluate the second derivative at both 0 and, the second derivative at both 1 and -1. So to do that, we first need to find the second derivative. So notice our second derivative at x is going to be equal to the derivative of the first derivative, and our first derivative is equal to 3x squared minus 3. So our second derivative is going to be 6x, and again, this is by the power rule. We're now going to evaluate the second derivative at both 1 and -1. So evaluating the second derivative at 1, we get that that's equal to 6 times 1, which is equal to 6, which is clearly greater than 0. And then we're going to evaluate at -1. And here we will get 6 times -1, which is equal to -6, which is less than 0. So what this tells us is, looking at the first point, our first point is going to occur when x is equal to 1, and then now we need to evaluate the function at 1. So evaluating g of x at 1, we get 1 cubed, which is just 1, minus 3, plus 1, which is going to be equal to -1. So that point, since our second derivative is strictly greater than 0, is a local min. And then similarly for the second one, if we evaluate our original function up here, our g of x at -1, we find that the point we're interested in is -1, 3, and this one is a local max. And again, it's a local max because that second derivative is less than 0. All right. Now in this example, notice that we didn't have to worry about where the derivative didn't exist because that first derivative existed everywhere. And then also we didn't have to worry about endpoints because we were looking at all of the real numbers. So next, let's look at an example where we are going to have to consider all 3 of those. So here we want to find the local extrema of g of x is equal to the absolute value of x squared minus 25, and we're going to be interested in the closed interval from -5 to 8. So the first thing that we're going to do is we're going to redefine g of x as a piecewise function to make this a little bit easier. So notice we can also define g of x as okay. So why does this work? And to see why this works, we can think of a number line. So notice that the interval that we're interested in is from -5 to 8. So the first thing I'm going to do is I'm just going to draw myself a number line from -5 to 8. All right. So first, let's look at the region from -5 to 5. Okay. So notice that any number in this region, once we square it, will be less than 25. And then any number outside of the region will be greater than 25. So why is this important? If we come up here and we look at the absolute value, notice we're interested in the absolute value of x squared minus 25. So for any value outside of the region, and I'm just going to shade this in purple. So for any value outside of that region, once I square that value and I subtract off 25, I'm going to end up with a positive number. And so I don't need to take the absolute value. I'll get that exact number. And so this is why you see in the first part of this piecewise function that for x's between 5 up to, between 5 and 8 rather, those values are always going to result in a positive value. So we just end up with the absolute value there. A positive number, so the absolute value doesn't matter. And so you'll notice in the piecewise function, we just have the x squared minus 25. On the other hand, for numbers that are in the yellow region, any of those values squared are actually going to be less than 25. So when we take that value minus 25, we're going to end up with a negative number, and the absolute value is going to make that positive. Well, we know that one way to make a negative number positive is to multiply it by -1. And so you'll notice for numbers that are in the yellow region, what we have here is actually x squared minus 25 times -1. So the 25 becomes positive and the x squared becomes negative. And so this is why we can write this absolute value function as a piecewise function. Now, one reason that we want to do this is it makes taking the derivative a little bit easier. So next, we're going to take the first derivative. And remember, the reason that we want to take the first derivative is we're trying to find all the candidates for these local extrema. And so again, if we go all the way back up to this first box, the very first thing we want to do is find all the points where the first derivative is equal to 0. So here, our first derivative, since this is a piecewise function, we can just take the first derivative of those pieces individually. And in both cases, we're going to use the power rule. So the first derivative of x squared minus 25 is going to be equal to 2x. And this is going to be the derivative for when x is greater than 5 and less than or equal to 8. And the derivative of the second piece, 25 minus x squared, is going to be equal to -2x. And this is going to be the derivative when x is greater than or equal to -5 or less than or equal to 5. So the first thing to notice here is that g of x is not differentiable at 5. And this is because the limit from the left is -10, and the limit from the right is 10. And we can see that by looking at the function. So I actually need to make a correction here at my how I've defined this derivative. And here I actually need to erase that equality sign. All right, so what this tells us is, again, if we go back up to that very first box, we're trying to find this candidate for our local extrema. We need to find all the points where the first derivative is equal to 0, and we need to find all the points where that first derivative does not exist. So this automatically tells me, since I know the derivative does not exist at 5, that's going to be one of the points that I need to check. So let's check where. So we're going to check the point where g of x is not differentiable, i.e. x equal to 5. So notice at x equals 5, g prime of x changes from negative to positive. And we can see that looking here. So if we were to evaluate at 5, as we move from negative 5 to 5, we would have a negative 10. And then as we move up from 5 to 8, we would have a 2. And so I'm realizing, looking at this, really when writing this piecewise function, I probably should have listed the bottom piece first, since we're moving from negative to positive 5 and then 5 to 8. So just know that probably would have been better if I switched those two in the order. All right, so for this reason, if we're moving from a negative to a positive, this tells me that the function evaluated at 5 is going to be a local minimum. And so looking at my function evaluated at 5, so here is my function. If we evaluate the function at 5, we get 25 minus 25, so we're going to have 0. And so that is one of my local extrema. So that's one point I need to consider. Now, remember though, I also still need to find the points where the derivative is equal to 0, and I need to check at the endpoints. So next, let's look at where the derivative is equal to 0. Okay. So notice that g prime of x, and so again, here is my g prime of x. The only way for g prime of x to be equal to 0 would be for x to be equal to 0. And so next we're going to use that second derivative test to help us figure out if at 0 do we have a minimum or a maximum. So we're going to evaluate g prime of x at 0. So notice that g prime of 0, the second derivative at 0, well, in order to find that, we actually need to find the second derivative first. So let's actually do that first. So looking at the second derivative of x, right here is our first derivative. So when x is between 5 and 8, the derivative with respect of 2x is just 2. And then when x is between negative 5 and 5, if we take the derivative of negative 2 with respect to x, we're just going to get negative 2. So here we have negative 5 less than or equal to x less than 5. So now if we want to find the second derivative evaluated at 0, we can see that that is equal to negative 2 because 0 falls in this interval right here. So therefore, since -2 is obviously less than 0, we're going to have a local max. So the point 0, and then we need to evaluate the function at 0. So notice the function evaluated at 0 is going to be equal to the absolute value of -25, which is just 25, is a local max. So we have found two of our extrema. The first one we found was where the derivative didn't exist. The second one is where the derivative is equal to 0. And so now we have one more thing that we need to check. And so we need to check the endpoints last. So at the left endpoint, we have that the first derivative evaluated at -5. And so remember here, if we look at where that left endpoint's coming from, we've restricted x to be between -5 and 8. So -5 is our left endpoint, 8 is our right endpoint. And here, since we're working with the endpoints, we can apply that first derivative rule that we saw at the very beginning of the note set. So this rule right here. So again, we're going to check those endpoints. We're going to evaluate our first derivative at our left endpoint, which is -5. And so notice that the first derivative evaluated at -5 is going to be equal to -2 times -5, which is going to be equal to 10, which is greater than 0. So this tells us we're going to have a local minimum. So therefore, if we evaluate the function at -5, we would see that that's equal to 0. That's going to be a local min. So that's another local extrema that we have found. And then last, we need to check the right endpoint. We're going to do the exact same thing using that first derivative test. So we evaluate that first derivative at 8. We see that's equal to 16, which is greater than 0. But this time, since we're evaluating the right endpoint and the right endpoint is positive, this tells us that we have a local max. So therefore, the function evaluated at 8 is equal to 39. That point is a local max. So we have found, using kind of our checklist of things to check, 4 local extrema between the points -5 and 8. So to make this a little bit more concrete, the last thing I want to do here is I want to actually look at a plot of this function, look at each of these points, and see if they are occurring at local minimums and maximums. So the first thing I'm going to do is I'm going to draw a vertical line at each of my endpoints. So my first endpoint was at -5, and on this graph, -5 occurs right here. My right endpoint was at 8, and so 8 occurs about right here. So we're interested in the function on this closed interval. So now let's go through and actually mark where each of these points that we found are. So the first point that we found was at 5, 0. So notice the point 5, 0 is right here, and that is a local minimum, and that's exactly what we found. Next, let's look at the point 0, 25. The point 0, 25 occurs right here, and notice that that is a local max. The point -5, 0 occurs right here, and that is a local minimum. And then finally, the point 839, which occurs about right here, is a local maximum. And so we've identified all the local extrema. And so in this case, we can see that 839 is not only a local maximum, but it is also the global maximum. and that the two local minimums are equal to one another in terms of, their distance along the y-axis. And so since those are equal to one another, there is not a unique global minimum. All right, so the very last thing that we are going to look at in this set of notes is going to be inflection points. And so a point where a function shifts from concave up to concave down or vice versa is known as an inflection point. And so inflection points are points where the concavity of a function changes. And we actually have a second derivative test that can help us with inflection points. If the function is twice differentiable and has an inflection point at x equals c, then the second derivative will be equal to 0. And so notice here, so if this in this picture, this were point c and it was the inflection point, we know that we have this second derivative test that tells us if x is greater than 0 or x is less than 0, it tells us whether we have concave up or concave down. But located in that rule, so if we go back up here, remember really this piece right here was about the concavity, there's no equality there. And that's because when that second derivative is equal to 0, that's where you're not concave up or concave down. That's where you have your inflection point. So let's look at an example. We're going to find the inflection points of g of x is equal to x cubed minus 2, where x is an element of the real numbers. So notice here, as we've seen before, that g prime of x is equal to 3x squared. And the second derivative of x is equal to 6x. Again, both of these are by the power rule. And since the second derivative of x is equal to 0 only at x equals 0, this is the only possible inflection point. And then further, if we notice that the second derivative changes from negative to positive, at x equals 0, we know that we have an inflection point. And how we can know that is we can evaluate that second derivative at points below and above 0. So for example, if we evaluate that second derivative at -1, we would get a -6. And if we evaluated a +1, we get a +6. And so that's how we can see that that second derivative is shifting from negative to positive. All right, let's look at one more example here. So again, we're going to determine all the inflection points. But this time our function is g of x is equal to e to the negative x squared. And we're only going to be concerned with it when x is greater than or equal to 0. So just like before, we need to find the first derivative. So notice here we have e to the negative x squared. So here we have two functions. We could consider e to the x, and we know the derivative of that is e to the x. But inside of that we have an inner function which is negative x squared, so we're going to have to apply the chain rule. So by the chain rule, g prime of x is going to be equal to e to the negative x squared. And again, that's because we know the derivative of e to the x is just e to the x. And then we need to multiply by the derivative of the inner function, which is negative x squared. And the derivative of negative x squared with respect to x is negative 2x. And then next, we need to find the second derivative. Well, notice to find the second derivative, we now have a product of two functions. So here we're going to have to apply both the product rule and the chain rule. And I will leave you to check this on your own, but you should find that that second derivative is equal to 4x squared minus 2 times e to the negative x squared. All right, so again, we're going to be looking for when the second derivative is equal to 0. And we're only concerned with when x is greater than or equal to 0. We see that the second derivative of x equals 0 only when (4 times x squared minus 2 is equal to 0. And why is that true? Well, that's because e to the negative x squared, that is never going to be equal to 0. That term can't be, so we have to have the 4x squared minus 2 equal to 0. And then you can solve this to find that that suggests that x is equal to 1 over the square root of 2. All right, and so next, we now need to look a little bit above and a little bit below to figure out the behavior of the second derivative on either side of 1 over the square root of 2. And so we could show that the second derivative is less than 0 when we have x between 0 and 1 over the square root of 2, and we have that the second derivative is greater than 0 when x is greater than 1 over the square root of 2. So therefore, there is an inflection point at x equals 1 over the square root of 2. All right, so this covers section 5.3. Section 5.4 of your textbook gives 6 different examples of applied optimization problems. I'd like you to read this section on your own. So in chapters 5.1 through 5.3, really what you're learning is the different tool set for the tools that you need to do an optimization problem. In other words, where's the minimum, where is the maximum? And so 5.4 goes through 6 examples of applied problems where you can actually take this information and use it in an applied way. And so again, I'd like you to read those examples on your own.